Dorea Express. So today we'll be looking at effect of substituent. Before we look at effect of substituent, I would like you to know what a substituent is. A substituent is an atom or a group of atoms that replaces a hydrogen in a substitution reaction. So a substituent can be either electron withdrawing. It can be either electron withdrawing or electron donating. So it is either an electron withdrawing group or an electron donating group. So when it's electron withdrawing group, it can either withdraw electron through inductive effect. This minus simply means it is withdrawn electron, and it can also withdraw through mesomeric effect. When it's electron donating, it can donate through inductive effect and it can also donate through mesomeric effect. So that's why we have the minus I, plus I, minus M, and the plus M. So that's it. So for a group to be electron withdrawing, for something to be electron withdrawing, it must have at least a positive charge on it. While for a group to be considered an electron donating group, it must have at least a lone pair or a negative charge. So example of electron withdrawing group, we have the popular group, nitro group, NO2 plus. Electron donating groups, we have the methoxy group, OCH2 group, we have the methoxy group, we have this group here. It's lone pair here. So, and we also have a special case, the halogens. So we'll look at this halogen at the end of this video. We'll look at the special case, the halogen. They can be electron withdrawing group and they can be electron donating group. So let us first of all look at electron withdrawing group using the nitro group as an example. So you recall that in electrophilic aromatic substitution, what happened here is that a hydrogen on the benzene ring is replaced with an electrophile. So the electrophile in this case is NO2 plus. Let's look at the nitration reaction. Nitration. So what we have in nitration is benzene reacting with plus HNO3 in the presence of H2SO4 to give us a benzene ring with the nitro group attached. So first of all, the first step of this reaction is attack of the electrophile. So before this electrophile is formed, that's NO2 plus, there's a reaction between HNO3 and H2SO4. So we have HNO3 in this manner, OH, O, O. So our H2SO4, we have H, O, S, O, 3H. So this is H2SO4. So if you recall, there will be a lone pair here. So what will happen is that this lone pair will attack this hydrogen and this bond will break. Then what will happen is that this HNO3 will now be N, O, will have something of this nature. We now have O having two hydrogens plus a positive charge. So what will now happen here is that this bond will break and this will go out as what? H2O. That's water. So what we'll be having here is NO with a positive charge. So this is how our NO2 plus is formed. So let's look at the mechanism of the reaction. So as we say, what will happen is that this is our benzene. You see the first step is attack of electrophile. So this is NO2 plus. what will happen is that this double bond here will attack this place. So we are going to have an intermediate which will be of this nature. This way, NO2. This will be a plus. Have a plus here. So this, in this form, we can have other intermediates, sigma intermediates, sigma complexes or Wheeland intermediates. So the next step will be loss of a proton, which will be by our O minus SO3H. That's H2SO4 that lost an electron. That loses a proton. So it will simply come and take a hydrogen here and the ring will form back. So we want to look at the effect of NO2 in a ring. The effect of NO2, is it an electron withdrawing or an electron donating group? So let's look at it. Oh, we have a benzene ring, for example, and we have NO2 group. So is this group an electron withdrawing or an electron donating group? So let's look at it this way. Is it an electron withdrawing group or an electron donating group? So we can have a plus charge here. You can see. So is it an electron withdrawing group or an electron donating group? As you see, we want this plus charge to be neutralized. So what will happen is that this electron from the ring will move to this place. Can you see it? The electron from this ring will move to this place. It will make this bond to break and this electron will come here. So as you can see, it withdrew electron from the ring. That's why we say it is an electron withdrawing group. And this effect is not a straight line effect. If it were to be a straight line effect, we would have said it is an inductive effect. So this is mesomeric effect, mesomerism. So what we'll have here is something like this. We'll have a plus charge here. We'll have O minus. So if you look at this structure very well, you can see that this is the nitro group. This is our auto position, our metal position, our para position. Here also we have auto, metal, para. So as you can see, by resonance, so we have the auto, metal and para position. If this electron here will be delocalized, when it moves to this place, we are going to notice that we'll have the positive charge now on the para position. This is what we're going to have. We are going to have the positive charge on the para position. So if you look at this, if you look at it closely, you will see that we have positive charges on the auto and para position. So the meaning of this is that any nucleophile, any electrophile that this ring want to attack, you will see that this auto and para position is it has been deactivated. It is having a positive charge. So these positions cannot attack an electrophile. So it is only the metal position that can attack an electrophile. That's why we say nitro group as an electron withdrawing group is deactivating auto and para position, and it is activating the metal position towards electrophilic substitution. So let's look at an electron donating group, the methoxy group, OCH3 group. So as you can see, this is an electron donating group. This electron donating group can donate electron to the ring through mesomeric effect. What will happen is that this lone pair will move to this place. So when this one moves to this place, this electron here will move here. So what we are going to have is something like this: OCH3 plus minus. So this is what we have. So this is what we have. So if this electron move to this place, what we are going to have will be this OCH3 plus, then we will have something here, have a positive charge here, or a positive charge, and the last resonance structure we have will be this OCH3 plus, and when this moves to this place. So if you look at this clearly, you see that the negative sign is at the ortho and the para positions. The ortho and the para position, that's to tell you that the ortho and the para position is charged. So this ortho and para position can attack any electrophile. That's why electron donating group activates the ortho and para position towards electrophilic aromatic substitution and deactivate the metal position. So as you can see, the metal position is not as charged as this place. So that's why it is activating the ring. So let's look at other electron withdrawing and electron donating groups. For example, we have methane, CH3. If you look at this group now, we have C with 4 hydrogens. Why is this an electron donating group? If you look at the electronegativity of carbon and hydrogen, when you compare it, you see that carbon is very electronegative. So what happens is that this will be partially negative compared to these hydrogens, which will be partially positive. So that is to tell you that most of the electron will be drawn to the carbon. So whenever this carbon is bonded to a benzene ring, what happens is that it donates electron to the ring. So as you can see, there is no negative sign on the carbon. So it simply donates electron to the ring through inductive effect. It is a plus I. It gives a plus I effect. It donates electron to the group through inductive effect, and this effect dies with distance. This effect dies with distance, and this is a very weak effect. So it is a weak electron donating group. Let's look at NH2. Let's look at NH2 to this group. As you can see, NH2, it has a lone pair. This will give an indication that it donates electron to the ring through mesomeric effect. It donates electron to the ring through mesomeric effect, activating the ortho and the para position. So let's look at the special case I told you about at the beginning of this video. We have the halogen groups. So halogens include fluorine, chlorine, bromine, and iodine. So as you can see, if we have the periodic table this way, you will see that fluorine is the most electronegative element, and the trend is this way with electronegativity of 4.0. So it is very electronegative. Whenever you have fluorine in a group, it can either donate electron or withdraw electron. For example, if you have fluorine attached to a group, so it can either withdraw electron because it is more electronegative than this carbon atom here. So it will be partially negative and this will be partially positive. So it is an electron withdrawing group through inductive effect, and it can also donate electron. It can also donate electron because what we have is something like this, something of this nature. So it can donate this lone pair. So halogen groups are they are minus I and plus N. That means they add electron to the ring by mesomerism, and they withdraw electron from the group by inductive effect. So the summary of everything is that we have electron withdrawing groups and we have electron donating group. So you can either donate electron through plus I, which is inductive, or plus M, and you can withdraw through minus I, minus inductive, which is a line effect, and minus M, minus through mesomeric effect. Example of electron withdrawing group, we say the nitro group, and this one we have the methoxy group, OCH group. And for you to be an electron donating group, you must have a negative sign or must have lone pairs. While for you to be an electron withdrawing group, you must have a negative charge. So I hope your confusion in effect of substituent is solved. And another thing you need to know is that in electrophilic substitution reactions, you need to know is that what happens is that in EAS, electrophilic aromatic substitution, you need to know that electron withdrawing group, what they do to the group is that they deactivate the group, and while electron donating group activate the group, they direct auto and para, while this is metal directing. Thank you for